So like, as I was telling you last time, kind of this week we're a little doing a bit more of a review. Maybe today we'll start like going over some material that we was new, but there are certain skills that we kind of have to get in place first before we can start doing more complicated stuff. My typical plan will be kind of, as I mentioned, like lecture for perhaps 1 hour, if all goes well, like then kind of like do the quiz right after that, take a break, and then when we come back, like we start working like on the group problems or club work problems, however you want to call it, so that like kind of at least half of the class is just dedicated for you to working problems. So yeah, once it's 1 hour, I'll just try to shut up and like just like move on to the next stuff. So today we have to start talking about equations, how to solve equations, which is like one of the most important things that you do in algebra. So just before we do that, a quick reminder of two properties that are going to be very, very useful for today. So if you remember last time on Monday, I told you that when you have a number, so A is going to be a number. The opposite of that number is called negative A, right? And the idea of A and its opposite is that when you add them together, you get zero. That's the key property of of minus A. So the key fact that you need to remember always is that negative A plus A equals zero, or which is also that A plus negative A equals zero. This is a little bit odd to write this way, kind of to have the plus and the minus next to one another. So typically you just write A minus A equals zero, right? And so these two things mean the same. Okay, so for example, just to write a couple of quick examples. Negative 3 plus 3 equals 0, or 3 minus 3 equals 0, and then you can do that for any number, like 1/3 minus 1/3 equals 0, minus 1/3 plus 1/3 equals 0. It's like and it goes on. Like so for any number, like this is always true. So this will be useful when we start solving equations, because sometimes when you have an equation, you want to kind of add the opposite of a number to each side of the equation and things like that to start creating like zeros. So this is like an important property about a number and its opposite. And the other important property, this has to do more with sums, like subtraction. The other important property is about multiplication. And so the other thing that you need to know is that if you have a number, so again, this is a number. The reciprocal of that number, I don't think I used that word last time, but the reciprocal of that number is 1/A. So this is what's called the reciprocal of A. Well, reciprocal of A. By the way, this number cannot be zero, but so zero. Okay, so the reciprocal of A had like the key fact about A and its reciprocal is that when you multiply them, you get 1. That's how they are kind of they work together. So the key fact is that A times its reciprocal gives you 1. So for example, 2 times 2 times 1/2 is 1. That's the same as 1/2 times 2, but also and the same happens with any other number that you also happens with negative numbers, by the way. So -4 times 1/-4 equals 1. And again, you can write it in the opposite order if you like. this also kind of works well, like this number can be a fraction itself, so kind of it's better to have it written out separately. So the reciprocal of a fraction, like you have a fraction. The reciprocal, basically what it does is swap the numerator with the denominator, so b over a is what you would call the reciprocal. Reciprocal of the fraction. So for example, and the same key property still works, so a divided the a over b times b over a gives you 1. So for example, 2/3 times 3/2 is 1. 5/3 times 3/5 is 1. Again, it also works with negative numbers, so or negative fractions, minus 4/3 times, like the reciprocal of offset. So this one, and you can keep going. So this, and this I'll use over and over and over and over and over and over today. So I thought just like I should write them down explicitly, for you to refer to that. Are those making sense? About this? I'll just copy them here so that I can refer to them throughout the class, but. So again, that's like very important thing, properties that will be handy from that. So the first type of equation that we want to solve are called linear equations, and actually we'll spend a lot of time talking about those equations in the course. They're kind of like the most basic equations that you can start with. So these equations, like the ones that I'll talk about today, there's only one variable that appears, which I'll call x. So this will be an equation. Here's an equation. One variable appears. Which I'll typically refer to as x. So I'll refer to that variable as just like common usage as x, which I'll call x. Okay, so for example, so here's an example of like the type of equation that I want to study today. I'm just trying to use the same equations like as the notes to try to follow that more carefully. So for example. This equation will be the type of equation we'll be talking about. So this would be called a linear equation. Okay, and how are you supposed to think of this? Let me see. So the way to think about this is that x is a number whose value you don't know, right? So here x, that's why it's called a variable, right? X is a variable. So by that it's like a number, that you don't know. Okay, and the way to think about the equation is that the equation can be either like true or false, depending on the value that you give to x. So the way to think about it is that this is something that becomes true or false depending on what x becomes, on what value for x to give. Is something. Depending on the values x takes. So just to give you an example, like let's say you take x to be 0, right? So let's say here I take um, x to be 0. So what happens with this equation? Like the equation was 5x plus 3 equals 0, right? But if I'm saying now that x is supposed to be 0, what that means is you can do like what you call like a substitution. You literally just replace the value of x inside of here, right? So you get 5 times 0 plus 3 equals 0, right? 5 times 0 is 0, like 0 times anything is 0. So you get here 0 plus 3 equals 0. And then 0 plus 3 is 3. So you are getting the 3 equals 0, right? Which we know is false, right? So this is not true. So this is false. So the way we refer to this is that we say that x equals 0 does not solve the equation because it doesn't make it true. So x equals 0 does not solve the equation. That makes sense. So far, so good. Um, but there is a value you can find, or there's a number you can find that does solve the equation. This magical number is called the solution. In this, and I'll kind of what we are going to discuss today is how to find those solutions. But for now, I'll just tell you what the answer is. Like, so the magical value is x equals negative 3/5. Okay. So if somehow you came up with that and like with that particular solution, or that particular proposal, what happens here? Like you get negative 3/5 instead of, sorry, I'll copy the equation again. So the equation was 5x plus 3, right? Equals 0. And so you get 5 times negative 3/5. Um, plus 3 equals 0. I guess I should have put this like, it's also related to one of these properties about multiplication with fractions, but if you have something like, what should I put here? I'll put it b times a over b. There's kind of like a partial cancellation property as well, where this just gives you a. So like if a number appears in both like a kind of like a numerator and the denominator, like you can get rid of it basically. So here, like the 5 appears on the top and the bottom, but that's another way to think about it. So it goes away and you just end up with negative 3 plus 3 equals 0. And that is like, like a number with its opposite adds to 0, then you get that 0 equals 0. And that is correct, right? So this is a correct statement. This is true. So x equals negative 3/5 solves the equation. And again, today, kind of like the purpose will be to discuss why did I know that this was a number that would solve the equation. But for now, if I give it to you, like if you're not sure whether it solves it or not, what you are allowed to do is to literally replace the variable with that value to see whether it says something that's true or false. If it says something true, then it solves the equation. If it says something false, then, then it does not solve the equation. Is that okay? Question about it? Okay, so let me give you a few, so the idea of a linear, what makes this equation linear, just to kind of like distinguish it from other types of equations we'll study later. So what makes this equation linear? So for a linear equation, actually, let me just start it working here. So how do you identify a linear equation? That's kind of what I want to get at. So how to identify a linear equation? Okay, so what happens for a linear equation is that the variable x can appear multiplied by some number, right? Like that's allowed, but what is not allowed is to have kind of higher powers of x in the equation. So for a linear equation, um, x is allowed to, x can be multiplied by numbers. But you can have higher powers of x. So, can have powers of x. So let me give you the kind of like a good list and a bad list. So like the good ones are like all linear. So for example, so all of these are linear. All are linear. Because again, like, the rule is that you look at the variable x and it is only allowed to appear multiplied by a number. So like x with 5 is fine, 3 with x is fine, 2 with x, that's fine, those are okay. Or with x, 3 with x, that's okay. Like each of them kind of satisfies the conditions. But if you have things like this, let's give you like a bad list. So like this. I don't know, you're good with it. These are not linear. Uh, Not linear. So what are the culprits here? Okay, x squared, right? But so I don't like that two here. Don't like these three. But like this is even more of a mess because like this two, which is problematic during the exponent, right? And this like fraction is scary. So like there are two reasons like that I don't like it. Okay, so scary fraction. So like in practice, you kind of recognize them. It's pretty like you don't have to overthink it. Like if there's something that if the x appears more complicated than just x, more likely than not, it's not linear. It's not a linear equation. Um, Now, okay, now this one is a bit more tricky. Let me think, what do you think, what do you say about this one? It's not as easy as it seems, like most of the time it is, but like it can be more complicated than that. Okay, so this one is a tricky question. How about so what would you say about this? Is it linear or not linear? Linear? You say linear? Just move the centers. Okay, it is, okay, it looks linear because only x to the kind of x to the one appeared, right? Like there are no higher powers of x. Someone could be kind of like worried because like there's like distraction, right? Like so that is kind of gives some concern. But the way I would characterize this equation is that it can be made linear. So I'll show like it can be rewritten in a way that is clear that it is a linear equation. That's how I would put it. So it's not like it's like the presentation is kind of like off, but it can be fixed so that it's kind of more obvious that it is a linear equation. So I'll kind of show you in a couple of minutes how to do that. But let's just leave it as it can be rewritten so that it becomes linear more in a more clear way. So it can be rewritten. And then it becomes linear more clear. Okay, so but again, like that's kind of like the exception to the rule. Like the majority of the equations, like the way you will be given to them, more like in this presentation. So like it would be more like direct to tell whether they're linear or not. So now what I'm going to spend some time on is telling you how do you solve these equations. So how do you solve a linear equation?
Just to be clear, on the question on the left, you can multiply both sides by 3x - 1, right?
Correct, yeah, and that's what fixes it, yes, like, that's how it would become linear, yes, like, that's what I'll do after, like, to do another example, but yes, like, that's the fix. Good, so the idea, like, to solve the linear equation is that, we're going to just, like, using addition or multiplication, like, uh, so like, we'll just do addition, multiplication, only these two operations. We will rewrite it, we will rewrite the equation. So that basically everything that has x appears to the left on the left hand side of the equation, and the terms that do not have x are on the right hand side. Let me just see how. So that all the terms, involving x appear on the left side. And the rest on the right side of the equation. And the terms without x. On the right side. And after you do that, then you can just solve for like, and then once you do have it in that format, you will, so this is kind of step one. And then step two is to make the coefficient in front of x one. And then you make the coefficient multiplying x equal to one. Okay. So let me do a few examples to show you how this would work in practice. Some can be tricky, actually. You'll see like with some of the ones that I'll do. Okay. So in practice, after you've done this a couple of times, you will get, maybe you have already to some extent, but you just end up getting used to it and then you can kind of skip some steps. But I'm going to write absolutely every single step that you would need to do so that it's super clear what, what's going on. So if you kind of read the instructions, the instructions are like, I want everything that has X on the left side of the equation. That's kind of like just like a cosmetic preference. Like, it looks nicer to have like the variable on the left side from, I guess, because we just kind of read from left to right. Uh, And then I want everything that does not have X to appear on the right side. That's kind of like the convention. So, you like, again, I'm going to work with each, fixing each issue one at a time. So this -2 is not supposed to be here because it's not next to anything with X. So I want it to appear on the other side. The way to do that is that this equation, like the point of an equation is that both sides are the same thing. So the idea is that if you have an equation, you can kind of do the same operation to each side of the equation, because like the point of an equation is that the left side is supposed to be the same as the right side. So if you add 2 to the left side, that should be the same as adding 2 to the right side. So why am I going to choose 2? Because 2 is the opposite of -2. So I'll do 2 minus 2 plus 4x, or actually, let me put it on the, I'll kind of like make it more clear. So I'll add both sides, so both sides of the equation 2. So now it looks more clear that I'm adding 2. Because if these two sides are the same, then like adding the same thing to them should produce the same result. Basically, that's how you should think about that. And then these, like the whole point of doing this, again, I'm kind of showing every single step. But the whole point of doing this is that the opposite number and its opposite kind of go away in the sense of becoming 0. So this gives you 0. And I mean, the sum is whatever it is. In this particular case, that just happens to be 3. Okay, so I don't like to loop this 0 here, so I'll just write this like 4x equals 2x plus 3. Okay, and now the equation looks more clean, like it's improving like, in the way it looks. The next step, so already everything that doesn't have x is already on the right side. That's taken care of. But the other condition that I asked for is that everything that has x should be on the left side of the equation. So I haven't taken care of that because there's still these 2x on the right side. Right, so to take care of that, I add the opposite of 2x to make a 0, just as I did with the 2. So I'll do 4x with minus, so I mean, it kind of looks a little bit weird like this, but I'll just put like, I'll just subtract it on both sides, but it's kind of like adding plus -2x, just looks like an after. Okay. And then, so 4x with minus 2x becomes just 2x. And then what's happening here? Like this two x with this negative two x goes away, so I'll just put a 0 as before. So you get 0 plus 3. Okay, so we're almost there. So you get 2x equals 3. Okay? So that already takes complete step 1, because everything with x is on the left side, everything with without x is on the right side. And then the last requirement is just to solve for x, which is what you would call solve for x, by making the coefficient in front of x at 1. So to make a coefficient in front of x at 1, you're kind of playing with the reciprocal of the numbers. So you can multiply both sides of the equation by the reciprocal of 2, because 2 is the coefficient I want to get rid of. The reciprocal of 2 is 1/2. So you do 1/2 times 2x equals 1/2 times 3. Okay, and that will give me that that already will give 1/2 times 2 gives you 1, so that will give you the x equals 3x. Okay, let's do the next one, which looks very silly, but it's actually, it does have something that you have to be careful about, if there are no questions about this. And then I'll return to this one later. I guess I still don't have to reverse this. Okay, so this one is important because it's very easy to make a mistake on this one. Sometimes like the equations which are the simplest to write are the ones where like you can make the most mistakes, because like they're so simple that you kind of overlook what's going on. So this one is like important. Okay, so I don't know if anyone wants to suggest the first step that we could do to solve this one. Yes.
Move the 2x over to the left, which will go into x equals 0.
Okay, perfect. Now, okay, that is going to be the correct solution. So let's do first like the correct solution, which is what you just said. So let me put here like the correct solution, and then I'll put like the common mistake, because it is super common to do the mistake that I'll write in a second. But the correct solution is to say, okay, let's just follow the instructions of moving like the stuff with x to the left side of the equation. So you can say 3x minus 2x equals, so you subtract 2x from both sides of the equation, right? And so what happens here, 3x minus 2x is just x, right? And then 2x minus 2x is just 0. So that would give x equals 0. Now, here's the very common mistake, like, it is very easy to overlook this. So here's like the incorrect solution and the common mistake that happens. And this is like super common, so that's why I'm kind of trying to make a big fuss out of this. Well, like, what's very common is that you say, okay, I have 3x equals 2x, right? And then you might think, well, let me just, like, multiply both sides by the reciprocal of x. Like, that is a common mistake. So you would say this times 1 over x equals 2x times 1 over x. Okay. Because if you do this, like, like it kind of like the intent is clear, hopefully, because x with the reciprocal becomes 1, right? Like under multiplication. So you would get here the 3 and then like x with this reciprocal becomes one, so you would get here that 3 = 2. Right, so you would say, oh, this is impossible, right, because 3 is not 2, so you would say, oh, this has no solutions, right? So then you conclude that this has no solutions. Right, and then you would have said, oh, this equation cannot be solved. But the issue is that in order to multiply by the reciprocal of a number, you need to know ahead of time that that number is not 0, possibly. And since we don't know anything about x could have been 0. In fact, like x happened to be 0. So you are not allowed to multiply by the reciprocal of a number unless you know for a fact that the number is not 0. So that is like where like the issue can appear, and this appears more times than you would think, like, it is like a very common mistake to make. So let me write in words like what the issue is. So what is the problem? So what was the issue with this approach? You can't multiply by the reciprocal of a number. Unless, does that make sense? Just to any questions about this. Okay, so just to go back to this like more weird looking equation, like how do you that I have written a few minutes ago. Like this is like the other example that I wanted to do about it. Um, so this would be like maybe examples together. So if you wanted to solve this one. X plus 1. Okay, so what I said is that it can be made linear. It doesn't look it's not super clear it's linear, but it can be made linear by kind of multiplying by the denominator on both sides so that that goes away. So what I can do here, and this is also another place where it's important to use parentheses. I'll kind of write it first, like without parentheses, and then with parentheses to kind of like, let me actually put it on this right side. So if you write the multiplication this way, this is incredibly confusing. Like because, for example, here you have the 5, and then you don't know, is this 5 multiplying just this 3x, or is the 5 multiplying 3x minus 1, right? So the idea is that actually the 5 is multiplying the entire expression because you're multiplying every side of the equation by 3x minus 1. So the 5 is affecting all of this. So that's where the parentheses come in. If you don't put parentheses here, it is a mess, like, to understand what's going on. Like, you may have like the right intent in your head, but it's not the perfect, like, it is easy to kind of misinterpret it, because then you could just think, oh, 5 is just times 3x and not 3x minus 1. And here, this is less confusing, like, it wouldn't cause that much of a confusion here, but just for safety measures, like, I would also be like, okay, put a parenthesis there as well. Although again, that is not as problematic as in this case, so it's easier to kind of not make a mistake on this end. But here is very easy, okay? And so if you write that, then you get what? You get the point of like multiplying, it's kind of like a small version of this property that I wrote at the beginning of class. Like, you multiply by the denominator on both sides, you just give the numerator. So you get 2x plus 1. And then what happens here? So that's why the parentheses are important, because then you have to use the distributive property to do the multiplication. So 5 with 3x gives you 15x, and 5 with -1 gives you -5. Okay. And then the next step, now this is clearly a linear equation. Now you took care of the issue, it's more apparent that it was linear to begin with. And so now you can solve it exactly the same way that I told you earlier, in the sense that what you do now means to, move everything with x to the left side and everything without x to the right side. So like, let's take care of the one first. So again, you add the opposite, or like subtract 1, if you want to think about it that way. Okay, so that gives you 2x. 1 with -1 gives you 0. So you get 2x equals 15x minus 6. And then what I'll do is just like move this to the other side by subtracting 15x on both sides. By the way, all these examples are in the class notes, just in case. So like, you don't need to copy them per se, but if you want, you can. But I'll kind of will try to write exactly the same ones that are there, so that it's easier to just keep track of that example. So these give you negative 13x. And okay, this goes away, and then you get -6. And then you multiply by the reciprocal here. So well, sorry, I think I'll need a little bit extra space to not make it super crowded. So the reciprocal of -13 is -1 of, the one, like the minus sign, it can be the denominator. You can also put it on the top. That's not important, but let's keep it here just to make it more clear. So I'll put -13 over x. And then I'll put -1/13. Oh, yeah. The minus sign has to be somewhere, either in the numerator or the denominator. That doesn't matter, but let's just put it in the denominator. Okay, and so that gives you x. Okay, this becomes 1, so we just put it back. And this like minuses and so on, so you get 6/13. And now that I look at my notes, I notice that when I multiply, I don't have to upload another version, because I made a typo here, so I'll fix it. I now realize I have a typo, so I'll upload a new version after class, because I actually, when I multiply, I didn't distribute, so I just wrote -1 instead of -5. So you see, like, it's easy to make those mistakes, like happens all the time. So, but yeah, once I have fixed that up, I'll upload a new version after class. Okay, just to kind of start wrapping up this part, what I wanted to tell you. So based on what like you have seen, like when you have a linear equation, like the rule of thumb, like what happens, sliding angle 99.9% of the time is that you just find a value for a single value for x. So that's how you should think about a linear equation. It has only one solution. That is like the appropriate way to think about this. So here's like some observations I know. So when solving a linear equation, in practice, or like I'll just write it 99.9% of the time, just to say like really that's what you should expect whenever you solve a linear equation. You will find a single value of x that solves the equation. So like the linear equation has a what you would call a unique solution. It's only one word that works. You will find only one value of x that works. Okay, there are kind of more silly cases where like two other things can happen. So there are two other things that happen, but are way more unlikely. So two other things can occur. So, but more like, let me put here again, that they're more unlikely. Okay, so the first one is that, that there could be no solution, like it is possible for the equation to have no solution. It is possible for there to be no solution. So what's an example where that happens? They're kind of very apparent that they don't have a solution, but it's still kind of good to see one in practice. So here's one where like there's no solution. Like if you have something like that, you subtract negative 3x on both sides, like 3x plus 1 minus 3x. Plus 5 minus 3x. Right, and then you just get that 1 equals 5, right? And there, like, I mean, here, like, you don't have to do anything else. That's clear enough that it's a problem, right? So for certain types of equations, which again, like almost never happens, like that's kind of not the interesting problem for you to work on. So, but it's kind of like, by the way, like just so you know that this can occur. It does happen if you ever take linear algebra. That does happen a lot more often, and that's an important thing because in linear algebra there are multiple equations that you're working at the same time. So then it does become a tricky question. But here, like when it's just like a single equation, there's not much to kind of like lose like sleep about. So like here, like impossible, right? So this is like an example of no solution. Right? Which again, like it's not kind of like what you should be expecting. Like in practice, when I give you a problem, you should just expect that there's a solution, but just so you know that can occur. And the other extreme, this is kind of nothing works. The entire like the extreme of nothing works is that everything works. So that's the opposite extreme. Is that every value, any number works. So the other case that can occur is that any value of x works. Any value for x works. So what's an example of that? Like again, I'm kind of giving you somewhat silly examples, but that's more or less how they look in practice. Like if you say something like x equals x, what sort of equation is that? Like like if you want, you can subtract both, like x on both sides to get that 0 equals 0. But
it is true, even if you look at it from the first line, it's always true that a number is equals itself, right? Like it's regardless of what the number is, it will always be itself. 3 = 3, 4 = 4, 5 = 5. So it doesn't matter what you plug in here for x, you will always get like something that's true. So this is true regardless of what x is, right? So this works for any value of what of x. Okay, so again, I wouldn't like lose any sleep over these, like, for all the problems that I'll give you, basically, this will happen, like, where there's actually a single solution that occurs. But, if like the equation is simple enough, then things can go wrong, and then like, either you get no solutions or like any number works. Okay, so this is for now, all that I need to say about equations which are linear in one variable. So just to kind of talk for a few more minutes and before moving on to the quiz, and then I'll let you do some problems. The next step, and that's where I'll focus more on tomorrow, so like it's not for today, but just wanted to give you a preamble for what's going to happen tomorrow. So the next step, which is tomorrow. So the goal for tomorrow, and here a lot of stuff will happen. So here we will have to go pretty slowly because like it's like already like an interesting situation. But tomorrow what we'll study are linear equations where there are two variables present. So tomorrow we'll do where there are two variables. So what do I mean by that? I mean equations that look like this. Like, here's some examples. Like if we have y = x + 1, that's like a linear equation with two variables, the variables being x and y here. You could also have an equation which is 2x + 3y = 5. That's another equation where like there are two variables, and it's linear because again x and y only appear to the power 1. You can have minus x plus 3y plus 2y = 10. You could have like x = 5y minus 4. Like, there are tons of like, you can even have things where you have to simplify a little bit more. You can have things like x plus y = 2y minus x plus 2. Okay, so that's another one. So there's like tons of different equations. Once you have two variables, like there's a lot more variability on how you want to write them. Okay. But so what happens in this case, let's actually just kind of give you like heads up for what's going to happen. So what's going to happen is that now it's not super clear what you mean by solving the equation because there are two variables. So the way you want to think about this is that once you give a value to one of the variables, then the other one you want to determine the correct, like, you want to solve for the remaining variable. So the way to think about these equations, like, let's just stick with y = x + 1. So the idea to have behind this, right, is that once you give a value to one of the variables, then you can solve for the remaining variable. Then you can solve for the remaining variable. But it doesn't make sense to kind of solve for both variables simultaneously. That's what I'm trying to say, like, because they're like two variables, like if you need actually two equations to do that. But it doesn't make sense. To try to solve for both variables at the same time, right? To solve. Okay, so what do I mean by this? Let's just make this a bit more concrete. So, if you have like an equation like this. Okay, then I can say. I have two variables, y and x. Let me give a particular value to one of those variables. Typically, you just give the value to x. That's how you think about it, just because of alphabetical preferences. So you say, okay, I want to take x equals 0, but that's your choice. You decide to make that choice. So I want to take x equals 0. Okay, and then by taking x equals 0, you are forcing y to be whatever it needs to be according to the equation. So you're asking y to become what, 0 plus 1, right? And so now y happens to be 1. Okay, because you decided to give x the value 0, right? Here's another example. If you had taken x to be -2, right? So I wanted x now to be -2. So what does y need to be? It needs like, if you want the equation to be true, it needs to be whatever the equation asks it to be. So like you put x equals -2 here, so you get -2 plus 1, and that gives you -1. Okay, and so my point is that here, let me put it in green actually. My point is that once you have chosen a particular value for x, then you can determine the value for y, and there's nothing special about giving a particular value for x. It's just more common, but you could also have decided to do it with y. So if I had taken if you had decided to take y to be 3, for example, right? If you take let me put it in green. If you take y to be 3, so what different. So if you take y to be 3, then what does x have to be? Whatever will make this equation work. So you put 3 now, and then you get x plus 1. And well, if you subtract 1 on both sides, you would find that x equals 2, right? So here you would get that 2 equals x. So I'm saying, like, you see, like, it kind of went backwards because like I chose like the value for y first, and then I got the value for x second. So it like, depending on which you give values to first, like the other one would get determined by that equation. And so like there are a couple of ways you could represent this. So here's one way to represent this, which is kind of convenient. Now you think about this like as like a table of like values. So like again, like the variables can represent like different quantities of interest. So like like it could be like if you have a sibling, one x could be your age, and like y could be the age of your brother if you're 1 year apart, something silly like that. So like there are tons of like different like ways to kind of think about like what these variables could be. But the idea is that one way to represent the information like of what we're doing now is that you kind of like on one column have x and the possible values x could take, So like 0, -2, 2, for example. And then on the second column, you would put like a corresponding value y takes. So we know that if you take x to be 0, y would be 1. If you take x to be -2, y would be -1. And if you take, well, when x happened to be 2, like we know that that was like in correspondence with y equals 3. Okay? Right, so that is one way to kind of like display the information about x and y, just like kind of like literally put like a table relating the two values, right? But here's the thing, like, is that making sense? Here's the thing, like the problem is like there's so many values you could take. You would never finish doing this, right? Like you could take -3, -4, -5. Also in what order you put them. Okay, yeah, maybe you want to put like, if you put them like kind of increasing like 0, 1, 2, 3, 4, 5, then what happens with the negative values? Then you would need to go up, 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 up. So like there's no really good way to fill this out except for a list of finite numbers. Like, if you have a 10 or 20 that you really care about, then yes, this is fine. But if you wanted to kind of represent everything like more in a more accurate way, what you have to do is turn to pictures. So that's where the pictures come in, and that's where the Cartesian plane gets used. So the idea, an alternative way to represent this information, that's kind of what, this is kind of what I'll start telling you about tomorrow. So an alternative way to represent this equation y equals x plus 1 is by drawing what's called the Cartesian plane. Is by drawing the Cartesian plane. And again, I'll say more about that tomorrow, but just to give you like an idea. What's going to happen? Okay, so what's going to happen here is that you kind of represent the values x can take as being on a line because of this number line business that we talked about on the first day. And then you take the value that y can take also as being values on the number on a different number line, and you choose these lines to be perpendicular to one another. That's kind of the key to make everything of this like kind of be nice. So for example, let's start with colors to see how you could show the data here. So if I take 0, I would do kind of like a matching game. So 0 on the number line, right? The value, actually, let me put a different one, like before doing that one, let's say, put 1 and 1 goes with 2, just to make it a bit more clear. So, when x happens to be 1 on the number line, right? The corresponding value for y should be 2. I'll put like a 2 here. Well, you kind of start to make them up to scale. I'll try to be a bit more. Careful. Here, 1 and then 2. So it's somewhere in here. Okay, so this number 1 for x corresponds to this number 2 for y. Let's do one. So this is here. And then let's do the one. Like if I put 2, that should go with 3. So 2. Okay. And let's do one of the negative ones. And then put -2. So -2 is somewhere in here. And -2 goes with -1. -1 somewhere here. Is that more or less, in sense how making the matching? And here is even something better that you can do. So this is already a way to represent like what's going on, which is cute, but you can make it even more interesting because then you can be like, okay, so. You have this value of 1 and this value of 2. What if you kind of draw kind of lines that go through these two values, which are perpendicular, kind of like following these two lines? They would meet at a point here. What if you do the same here? You choose a line that's kind of parallel to this line and another line that's parallel to the other one. And then you get a point here. And then you choose a line for the green one and then another line for this value. And so it's like instead of like matching with the colors, because like you would also run out of colors, right? What you would do like is kind of choose like a point to represent like these two values. So you represent the two values as a single point on what is called this plane, okay? And then the convention, the convention is, and again, I'll kind of replay some of this tomorrow, but the convention is like, you kind of, again, kind of following the alphabetical order. To refer to this value, you would write 1, 2, because this is like the x value, this is the y value. This is 2, 3, because this is the x value, this is the y value. And this would be what you call the point -2, -1, because this is the x value and the y value. Okay, so the way this is always goes is that x value, y value, x value, y value. So for example, if I wrote something like, something like here, let's see. If I wrote something like this. So like here, this would be the 3, 4. 3, 4 means that the x value was 3. So you go down to the x value, and the 4 means that the y value would be 4. Okay. And I don't know if you kind of see like a pattern kind of falling in line, no pun intended, but if you keep doing this for many different values, these points, the following will happen. So I love using GeoGebra. I use it a lot during class. So what I like about it is that it's free. You don't have to download anything on the computer. You can do it online. So you just go to geogebra.org. And so, for example, just to show you how it looks, because it's kind of very useful, especially for this course to get used to like that. You click on calculator, you click on graphing calculator, okay? And so you could do 1, 2, then you could do 2, 3. Then you could do 3, 4. Those are the points, and then -2 and -1. So those are the exact same 4 points that I drew on the board. It's just like with different colors because like it would take me forever to change the colors on the animation. So if you keep doing this, actually I can do something fun for you if you want to see it this way. It's very So now I'm kind of going to, this is going to be what controls the values for X that I want to choose. It's just that like the animation doesn't allow me to put X, name this X. So if X equals 1, that is that point. If X equals 2, you are at this point. If X equals 3, that was that point. And if I start moving this around, right, like different values for like, X, you get a corresponding value for Y, you get a corresponding point. And this all will look like what? It will look like a line. Okay. So a linear equation looks like a line because like, the name is not like a surprise, like it is designed so that it matches with that. Okay, so what I'll tell you, like what we'll do tomorrow, okay, I'll tell you a little bit more about how do you put things on the plane, like this Cartesian plane. For example, this is called, if you look at these two lines, which are called the x-axis and the y-axis, they break the plane into 4 pieces. So this is called the first quadrant, second quadrant, third quadrant, fourth quadrant. And then we'll talk about like lines. So how do lines look in general? So there are a bunch of properties about lines, or these equations that become very clear once you know how to draw them here. So that's kind of like hopefully that is a little bit more new material, like, but it is kind of like one of the most important things of the course because lines are really, really important. So, like I'll try to see if I can like a YouTube video for you to watch about lines. But like just if you like art, just to tell you why lines matter. You can draw like the most beautiful curve in the world that you like very clearly, but then you can choose point, 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 point. You choose a bunch of points on this curve, and if you connect these points with lines, if you chose the points close enough, that all these mini lines are pretty close enough to the actual curve. So that is a way to kind of computer graphics how they work, right? Like you can't think about like doing like a curve. You don't expect the computer to actually do the curve. Like what it would do is kind of do all of these mini lines. It's just that once they become so close together, the human eye cannot really distinguish between the mini lines and the actual curve. And so they're like these Bezier curves that you can use everywhere in Adobe Illustrator, like Final Fantasy games, like anything you name it, whatever, like anything of electronics uses lines, like basically, because they are like various approximations for curves and many other things. Okay, so like lines are really important. So like that will be a good place to start. So I think that for today, like, yeah, that's kind of what I wanted to say. Are there any questions? Okay, so let me give you the quiz and then I think the quiz should be fast, but like if you finish early, then you can go out, take a break, and then we would return like a couple of minutes for you to start working on certain problems.